So this is going to be episode number 20 in the series of learning by doing MPI. And today we're going to talk about chapter 7 of the standard, which is about groups, context, communicators, and caching. We have a lot of stuff to cover in this chapter. The drill is going to be the same. I have no clue how many parts we're going to need for this chapter, but we are going to chop off every episode into basically chunks of 24 to 25-ish minutes of content, and then we're going to stop and then proceed to the next part. So I don't know how many parts we're going to need. As I said, we're going to go along with the content of this chapter. And then after every 25 minutes, I have a timer beside me. Every 24, 25-ish minutes, we're going to go into the next episode or next part. Before jumping into the content of this chapter, I wanted to also mention a sort of oversight or a mistake that we made when we were talking about collective communication. So if I go back in collective communications, for example, in blocking, I have corrected all the mistakes that I have made, but I kept only one intact to show you that what kind of oversight we made here. Let's take a look at all gather inter. So this mistake was happening when we were talking about the scenarios that we had this inter-communicator scenarios, right? So let's go down. If you go down to the code on line 51, for example, when we want to basically have a receive buffer, which is going to be dynamically allocated with a call to malloc, so basically color 0 is group A, and color and else is basically group B, right? So we said if we want to dynamically allocate based on the size of group B when you're in group A, you need to say world size minus local size. But on the contrary, we said in our explanation probably a week ago or so when we had this collective communication, then we said in group B, you need to pass in local size here. And this is basically a little bit stupid, you know, because local size, no matter what, is going to basically reflect the local size. If you're in group A, it's going to give you the local size in group A. So how many processes are in group A? If you're in group B, local size is going to give you the size of processes that you have in group B. So let me show you what kind of effect it makes. As we also basically stressed on this fact that this is not going to matter when you are using even number of processes, it's not going to matter. Take a look at this. If I say MPI, CC, MPI all gather, inter, and if I say MPI run minus NP4, for example, with even number of processes, you see that the result is completely fine because these are basically proc 0 and proc 1 are in group A. They have information from group B, which is processes 2 and 3. These are the ranks of those processes, right? And group B also has correctly information about group A, which are processes 0 and 1. And that is how basically this array is basically filled. But if I take a look at this, if I say MPI run minus NP5, if I use odd number of processes, take a look at this. You see a 650 here and a 3 here and a 3 here. What the heck is that? So going back here, as I said, here the solution for that or the remedy for this oversight or mistake is that we add a parentheses, world size, minus local size. So this is going to be exactly as the code above. And when you are printing results, you need to also make sure that here you don't go up to local size. You should go up to world size minus local size. And here, world size minus local size. So this is going to be the solution that you need to basically make in other areas that we made the same mistake. I have basically tracked all the source codes or of the examples that were affected by this. So let's first compile this and see if it works. MPICC and then MPI run. You see that now correctly we have information. These are processes in group A, process 0 and process 1. They have information from processes in group B, which is 2, 3, and 4. These are the ranks of processes in group B. And processes in group B, the first one here, has information 0 and 1 from processes in group A. And process 3 and 4 also have this thing. And notice that these processes 2, 3, and 4, in the previous version, they had 3 elements for this buffer. And we were accessing something which was not properly initialized, and that is why we get a 650 there, or we get a like random junk number there. It could be any number there. But in reality, processes in group B actually should get only 2 buffers, because processes in group A only have 2 members, proc0 and proc1. So this is the solution for that mistake. And on a piece of paper, I am going to read to you all sort of the source code examples that basically were affected by the same sort of mistake. So if you are watching the collective communication video series, I think we had 11 parts in those series. Make sure that you basically, if you write these codes somewhere for yourself, make sure that you also apply the same kind of fix or the same kind of remedy. So these are the affected source code examples. MPI all gather inter, this is the one that we fixed right now. MPI all gather v inter, MPI all to all inter, MPI all to all v inter, MPI all to all w inter, MPI reduces scatter block inter, MPI reduces scatter inter. So these are all the source code examples, these 7 categories of examples. Actually, you need to multiply 7 by 3 because we had blocking, we had non-blocking, and we had persistent sort of operations. So, and we had also reduced operations. We had only 2 in reduced operations. MPI reduces scatter block inter and MPI reduces scatter inter, which we had, if you go inside reduce operations, in there you also had blocking, non-blocking, and persistent. So make sure that that kind of fix needs to be there for those examples. And the oversight was basically when you are in group B, the local size is going to give you the size of group B, and when you are in group A, the local size is going to give you the size of group A. So now we can basically safely go back to groups, contexts, and communicators. These are the list of the examples that we have. And we are going to jump into this chapter. Let's start with the introduction. This chapter introduces MPI features that support the development of parallel libraries. Parallel libraries are needed to encapsulate the distracting complications inherent in parallel implementations of key algorithms. They help to ensure consistent correctness of such procedures and provide a higher level of portability than MPI itself can provide. As such, libraries prevent each programmer from repeating the work of defining consistent data structures, data layouts, and methods that implement key algorithms, for example, like matrix operation and stuff like that. Since the best libraries come with several variations on parallel systems, for example, you have different data layouts, you have different strategies depending on the size of the system or the size of the problem even, or you have a different type of floating point, this too needs to be hidden from the user. So if you're interested, you got to go to basically these, whoops, I didn't mean to do that. You got to go to references number 5 and number 63. This is on MPI 4.1 for further information on those. But this is features needed to support libraries. Safe communication space that guarantees that libraries can communicate as they need to without conflicting with communication extraneous to the library. So whatever communication is happening inside an MPI library should be safely guaranteed. That communication space needs to be safely guaranteed to not interfere with whatever communication that is happening outside of the library. So that's the first feature. The second one is group scope for collective operations that allow libraries to avoid unnecessarily synchronizing uninvolved MPI processes. That's very, very important. Abstract naming of MPI processes to allow libraries to describe their communication in terms suitable to their own data structures and algorithms. The ability to adorn basically means to make it beautiful or make it nicer, a set of communicating MPI processes with additional user-defined attributes such as extra collective operations. This mechanism should provide a means for the user or library writer to effectively basically extend message passing notation. Okay. So MPI support for libraries. These are basically to be able to basically have robust libraries. MPI basically provides you these sort of concepts. And these are the concepts that we want to talk about today. Context of communication, groups of MPI processes, virtual topologies. We haven't talked about that. That's the subject of chapter 8 or the next chapter. Attribute caching, and then communicators. So communicators, see these references, 236165, encapsulate all of these ideas in order to provide the appropriate scope for all communication operations in MPI. Communicators are divided into two kinds of intra-communicator for operations within a single group of processes and inter-communicator for operations between two group of MPI processes. So we have already seen, or we already know this idea of inter-communicator and intra-communicator when we were talking about collective communication. Caching. Communicators provide a caching mechanism that allows one to associate new attributes with communicators on par with MPI built-in features. This can be used by advanced users to adorn communicators further, and by MPI to implement some communicator functions. For example, the virtual topology functions described in Chapter 8 are likely to be supported this way. Groups. Groups define an ordered collection of MPI processes, each within a rank, and it is this group that defines the low-level names or ranks for communication. Thus, groups define a scope for MPI process names in point-to-point communication. In addition, groups define the scope of collective operations. Groups may be manipulated separately from communicators, but only and only we use communicators in communications. Intra-communicators. The most commonly used means for message passing in MPI is via intra-communicators. Intra-communicators contain an instance of a group, context of a communication for both point-to-point and collective communication, and the ability to include virtual topology and other attributes. These features work as follows. So take a look at context. Contexts provide the ability to have separate safe universes of message passing in MPI. So this is super important. Contexts are not explicit objects, but they are sort of, let's say, some additional tags or means in which you can distinguish, for example, point-to-point communications and collective communications. You remember when we were talking about collective communications, we said that MPI guarantees that communication happening in point-to-point communication is not going to interfere with communication which is happening in collective sort of operation routines. So this is with the help of context. A context is akin to an additional tag, this is what we said, that differentiates messages. The system manages this differentiation process. The use of separate communication contexts by distinct libraries or distinct library invocations insulates communication internal to the library execution from external communications. This allows the invocation of the library even if there are pending communication operations or decoupled MPI activities on other communicators, and avoids the need to synchronize entry or exit points into the library code. Pending communication or decoupled MPI activities of point-to-point operations are also guaranteed not to interfere with collective communication operations within a single communicator. So we're not going to have interference with this context. We're not going to have interference when we are talking about different communicators, communication in different communicators, and within a single communicator, we are not going to have interference, for example, between point-to-point communications and collective communications. Groups define the participants in the communication, see above, of a communicator. A virtual topology defines a special mapping of MPI processes ranks in a group to and from a topology. Special constructors for communicators are defined in Chapter 8 to provide this feature, and intra-communicators are, as described in this chapter, do not have topologies. Attributes define the local information that the user or library has added to a communicator for later reference. So we have an advice to users. Let's read this as well. The practice in many communication libraries is that there is a unique predefined communication universe that includes all MPI processes available when the parallel program is initiated. And that we already know what that is. That's MPI world. The MPI processes are assigned consecutive ranks. Participants in a point-to-point communication are identified by their rank. A collective communication, such as broadcast, always involves all MPI processes. When using the world model, this is the only model that we use so far in all the basically video series that we have for MPI. The session model is, I think, a subject of chapter 11, as it also shows it here, section 11.2. This practice can be followed by MPI by using the predefined communicator MPI world. Okay, nice. Now let's jump into inter-communicators. The discussion has dealt so far with intra-communicators, communication within a group. MPI also supports inter-communication, communication between two non-overlapping groups. That is super, super important. They have to be non-overlapping. When an application is built by composing several parallel modules, it is convenient to allow one module to communicate with another using local ranks for addressing within the second module. This is especially convenient in a client-server computing paradigm where either client or server are parallel. Okay, I think maybe we should not read the rest of it. Let's see. The support of inter-communicator also provides a mechanism for the extension of MPI to a dynamic model where not all MPI processes are pre-allocated at initialization time. Oh, this is also another sort of model of parallel programming, because we can have also dynamic model, which means that in all of our examples, the number of processes that we assign in the beginning is not going to change throughout the execution of the program. So let's say if we run, for example, MPI run minus NP5, throughout the execution of the program, we're going to have 5 processes. That's it. We're not going to have any addition or subtraction of those number of processes. But in dynamic model, you have it basically. You can have different number of processes. In such a situation, it becomes necessary to support communication across universes. Inter-communication is supported by objects called inter-communicators. Okay, let's not read the rest of it. Let's jump into this. Contexts provide the ability to have a separate safe universe of message passing between two groups. This is similar to what we had in intra-communicators, right? So we're going to talk about context first. So a send operation in the local group is always matched by a receive operation in the remote group and vice versa. So if like local group, you can imagine in your mind as group A, or left group when we were talking about collective communications. And then remote group was basically right group or group B that we called it. The system manages this differentiation process. The use of separate communication context by distinct libraries or distinct library invocations insulates communication internal to the library and from the external ones, from the external communications. So again, this text is going to be similar to what we had in intra-communicators. I'm not going to read everything again. One thing which is different is that virtual topology is undefined for an inter-communicator. So we're not going to have any virtual topologies in inter-communicators. As before, also attributes cache defines the local information that the user or library has added to a communicator for later reference. Okay, now let's jump into basic concepts, which whatever we have learned so far about, I don't know, context, intra-communicators, inter-communicators, and caching and stuff like that, now we're going to have a more formal sort of definition for those terms. Okay, it says return a more formal definition to these concepts introduced above. We start with groups. A group is an ordered set of MPI process identifiers, henceforth MPI processes. MPI processes are implementation-dependent objects. Each MPI process in a group is associated with an integer rank. Ranks are consecutive and start from 0, and they go up to size -1, size being the total number of processes used. Groups are represented by opaque group objects and hence cannot be directly transferred from one MPI process to another. A group is used within a communicator to describe the participants in a communication universe and to rank such participants, thus giving them unique names within that universe of communication. There's a special predefined group called MPI group empty, which is a group with no members. So if you want to have a group with a dummy group with no members, you're going to use this MPI group empty. But you have to distinguish this MPI group empty from MPI group null, which is actually an invalid group handle. What is the difference? The difference is that MPI group empty is a valid handle. So in those operations or functions or routines or procedures that they want an argument of groups, you can use MPI group empty. But in those procedures and routines, if you pass in MPI group null, it's not going to work because MPI group null is an invalid group handle. So that's the major difference. And that is, I think, the subject of this advice to users, I think. Yes. Now we move on to contexts. A context is a property of communicators that allows partitioning of the communicator space. A message sent in one context cannot be received in another context. Furthermore, where permitted, collective operations are independent of pending point-to-point communications or operations and decoupled MPI activities, point-to-point operations. Contexts are not explicit MPI objects. This is what we mentioned earlier. They appear only as part of the realization of communicators. Okay, safety means that collective and point-to-point communications within one communicator do not interfere. This we already mentioned it. And that communication over distinct communicators do not interfere. This we also mentioned. So communications happening in two distinct communicators should not or must not interfere with each other. And within a single communicator, point-to-point operations and collective operations should not interfere as well, or must not interfere as well. We already mentioned those things. Okay. It says, since contexts are not explicit objects, other implementations are also possible. Okay, we're not going to read everything here. Intra-communicators. Intra-communicators bring together the concepts of groups and contexts. To support implementation of specific optimizations and application topologies defined in the next chapter, chapter 8, communicators may also cache additional information. That is, later in this chapter, we're going to see that in section 7.7. MPI communication operations reference communicators to determine the scope and the communication universe in which a point-to-point or collective operation is to operate. We go here. Intra-communicators are represented by opaque intra-communicator objects and hence cannot be directly transferred from one MPI process to another. Next one is predefined intra-communicators. When using the world model, that's the one that we have used so far for MPI initialization, and an initial intra-communicator MPI come world of all MPI processes the local MPI process can communicate with after initialization, itself included, is defined once MPI init or MPI init thread has been called. In addition, the communicator MPI come self is provided, which includes only the MPI process itself. When using the session model, we don't care about this one because that's the subject of basically chapter 11. So let's not delve into that. The predefined constant MPI come null is also an invalid communicator handle. So similar to MPI group null, we have MPI come null, which is an invalid communicator handle. In a static process model implementation, we talked about dynamic process model. We said that the number of processes can change throughout the execution of that program. But in a static process model, the number of processes are not going to change in an MPI application. So it says, in a static process model implementation of MPI, all MPI processes that participate in the computation are available after MPI. Whoops. So 25 minutes are over. I'm going to stop right here, and we're going to continue in the next part.